Hello everyone, I'm Dingji from Shanghai Jiao University. This talk will introduce our work TwinVisor, the first system that enables hardware-isolated confidential VMs for ARM platforms. Data security is very important. In the context of cloud computing, more and more data is being moved to the public cloud. Tenants are entrusting data with cloud services. But data breach is a daily occurrence. For example, Microsoft Azure Cloud Database was breached due to misconfiguration last year, exposing 250 million entries of sensitive data. Therefore, regulations such as GDPR has been put into effect to enforce data security standards. Confidential computing leverages hardware-isolated execution environments to ensure that sensitive data is only accessible to authorized code. Secure enclaves, the application-level confidential computing, are deployed in cloud to protect tenants' data. For example, Azure provides Intel SGX-based secure database. Confidential VM is another type of confidential computing that offers an OS-level isolation. It has recently gained traction due to its good compatibility, minimal intrusiveness, and the clear security boundary. As a result, major cloud vendors such as Google Cloud, Microsoft Azure, and IBM Cloud are now offering AMD SEV-based confidential VMs. Existing confidential VM solutions mainly leverage specialized hardware to isolate VMs upon a shared hypervisor. For example, AMD SEV deploys a dedicated secure processor to take care of VMs, whereas Intel TDX employs a microcode implemented hardware shim called TDX module to monitor the interactions between the VM and the untrusted hypervisor. Besides, IBM PEF has a new hardware privilege level with a software shim layer called UltraVisor to enforce security policies. With the rise of cloud computing, the ARM platform has become popular in data centers due to its rich ecosystem and excellent price-performance ratio. Cloud providers such as AWS and Huawei Cloud have offered ARM platforms for their tenants. Apparently, users of ARM platforms care about the security of their sensitive data as well, but there is no available confidential VM solution on ARM yet. Therefore, it is natural for security-sensitive ARM users to concern about when and how ARM servers will support confidential VMs. On the other hand, ARM already has a widely used hardware extension named TrustZone, which isolates the secure world from the normal world on ARM server. Region-based memory isolation is supported by the hardware. Besides, the secure EL2 extension is supported in TrustZone since ARM v8.4, which mirrors almost all aspects of NEL2 to enable hardware virtualization in the secure world. This leads to a core question. Is it possible to support confidential VMs on ARM servers by retrofitting TrustZone with new software designs? A straightforward design of TrustZone-style is to deploy a dedicated, full-fledged hypervisor in TrustZone to run secure VMs. But lessons from commercial hypervisors and TE kernels tell us that this method is inadequate. Both of them were born with a small TCP that has a high security guarantee, but eventually evolved into a bloated TCP with numerous security vulnerabilities and large attack surfaces. Tables below list some representative CVEs of KVM and TE systems. Therefore, we propose TwinVisor. A key observation is that mature hypervisors such as KVM ARM already exist in the normal world. The design of TwinVisor disentangles the management from the protection. As shown in the figure, TwinVisor reuses the existing hypervisor as the N-visor in the normal world to manage hardware resources and serve both secure VMs and normal VMs. In terms of protection, TwinVisor creates a tiny hypervisor as the S-visor in the secure world to focus on protecting S-VMs. In this way, the TCP of S-visor keeps small despite the evolution of the N-visor. In TwinVisor's threat model, only the S-visor and the firmware are trusted software. NVMs and the N-visor can be compromised by attackers, while S-VMs may be controlled by malicious tenants. Defense methods against physical, side-channel, and denial-of-service attacks are orthogonal to the design of TwinVisor. TwinVisor also assumes that device vendors provide hardware-backed root of trust for attestation, and S-VMs protect their own I/O data with encryption and integrity checking. To open the secure world to confidential VMs, there are 3 goals. For security, we need to protect S-VMs from untrusted software and keep the TCP small all the time so that it can be easily verified. For efficiency, S-VMs should achieve comparable performance and scalability to vanilla. For ease of use, we must introduce minor modifications to existing software. Nevertheless, existing TrustZone hardware was not originally designed for confidential VMs, which poses 3 major challenges for TwinVisor. First, the secure world in which the S-visor resides is no more privileged than the normal world, making it impossible for the S-visor to trap and emulate sensitive instructions executed by the N-visor transparently. An ideal hardware support may put the S-visor in a higher privilege than the N-visor for monitoring. Second, traditional TrustZone applications have fixed resource requirements, so that TrustZone adopts a static policy of resource partition. However, S-VM's usage of hardware resources is highly dynamic. The static resource partition results in insufficient resources if one type of memory is used up, or low resource utilization if the number of contiguous memory regions exceeds the hardware limit. Third, conventional TrustZone usage model is based on the assumption that word switches are infrequent, so that a large switch overhead has little impact on the overall performance. But frequent communications between the N-visor and the S-visor due to VM access can cause much runtime overhead for S-VMs. A possible solution for the first challenge is a paravirtualized model that replaces all sensitive operations in the N-visor with APIs provided by the S-visor. For example, one can replace operations such as modifying system registers and updating stage 2 page tables with SMC instructions. When the N-visor attempts to execute such operations, it will request the S-visor for emulation. But this method involves too many word switches and excessively modifies the N-visor. A key observation is that any configurations done by the N-visor cannot affect the NS-VM until the S-visor starts to run this VM, logically making the N-visor less privileged than the S-visor. Therefore, we propose a horizontal trap to batch all checks on N-visor's configurations until the S-visor enters the S-VM. In particular, TwinVisor provides a call gate for the N-visor to proactively enter the S-visor, and only replaces e-return instructions for VM resume with SMC instructions, which reduces word switches with minor modifications. The registers and memory mappings are checked in place by the S-visor, so that the N-visor and the S-visor do not need to communicate through any PV data structures. To prevent the N-visor from accessing sensitive data stored in registers, the S-visor selectively exposes general-purpose register values before redirecting a VM exit to the N-visor. In addition, the S-visor validates system registers before resuming an SVM. Take an MMIO exit from the SVM as an example. The S-visor intercepts the VM exit and has the value of X1 and X2 registers before redirecting to the N-visor. As a result, only X3 is exposed to the N-visor. TwinVisor also guarantees that the N-visor cannot maliciously change an SVM's memory view by building a shadow stage 2 page table in the secure memory. To reduce the N-visor to handle stage 2 page faults normally, the N-visor is still able to modify the normal S2PT of each SVM. After the N-visor adds the new mapping into the normal S2PT, it invokes the call gate to forward the control flow to the S-visor. The S-visor checks and synchronizes the new mapping to the shadow S2PT, and finally resumes the SVM. To address the second challenge, we need to support fine-grained dynamic resource adjustments. Unfortunately, there is a mismatch between S-VMs' discrete memory pages and existing TrustZone's limited contiguous secure memory regions, which easily leads to a waste of memory or insufficient secure memory regions. In the left figure, though the red memory page in the middle is not used by the S-VM, it cannot be changed to the normal memory, because the region-based secure memory region is unable to adjust memory security attribute in a fine-grained way. Moreover, N-visors unaware of dynamic adjustment of memory security can result in memory access fault. In the right figure, assume that the S-visor newly changes a memory page from normal to secure. If the N-visor is unaware of this change, it may still try to access this page, which will trigger a fault taken to EL3. Fortunately, we observe that today's OSs are usually equipped with contiguous memory allocators that can allocate consecutive physical pages at a large scale. Thus, we propose Split CMA, which cooperates the N-visor and the S-visor together to keep secure memory contiguous. This figure shows the process of a memory allocation of Split CMA. First, a stage 2 page fault happens from SVM1. The S-visor forwards the fault information to the N-visor. Then the N-visor starts to allocate a new page at the end of the secure memory region. Next, the Split CMA part in the N-visor finds that the page at the end of the secure memory region is already occupied by an N-VM, so that it migrates the page content to another location. After the migration, the page is ready for SVM1 now. The Split CMA part in the S-visor adds the page to secure memory by enlarging the secure memory region. Next, we show another example of memory compaction of the Split CMA. At a time, the SVM1 shuts down, and thus leaves some unused pages in the secure memory region. Assume that the N-visor tries to build some new NVMs and requires much more normal memory, only to find that there is not enough normal memory. Then the N-visor tells the Split CMA, which cooperates S-visor and N-visor, to compact unused pages in the secure memory region. After the compaction, the S-visor resizes the secure memory region, after which there is enough normal memory for new NVMs now. Please refer to our paper for more examples and details of Split CMA. To mitigate the third performance issue, we find that a word switch contains redundant operations like repeatedly saving and restoring the register values of a vCPU when entering and exiting EL3 and SEL2. These operations incur large overhead as shown in our evaluation. So we design a fast switch facility that reduces the latency of a word switch by 37%. By saving general-purpose registers in the shared memory between the N-visor and the S-visor, TwinVisor removes redundant switches and memory copies of general-purpose registers. With register inheritance, TwinVisor keeps system registers untouched during the word switch to further reduce latency. While previous work used a combination of set call pooling and shared memory to avoid context switches, this method wastes CPU resources. Furthermore, it is difficult to determine the appropriate number of cores dedicated to pooling. Now let's summarize the key techniques of TwinVisor. To tackle the independent privilege models, we propose H-trap that logically deprivileges the N-visor with minor modifications. To deal with the static resource partitions, we propose a Split CMA that cooperates the S-visor and the N-visor together to dynamically maintain secure memory pages in a contiguous way to fit the limited number of the secure memory regions. To mitigate the slow but frequent word switches, we propose fast switch that reduces the word switch latency by avoiding redundant operations. Please refer to our paper for more details. The techniques mentioned before guarantee the security of SVM's registers and memory. In addition, TwinVisor also has to protect the I/O of S-VMs. Similar to previous work, we implemented shadow PVIO to reuse existing PVIO code and be transparent to S-VMs. The problem is that the N-visor cannot access the PVIO rings and DMA buffers of S-VMs, because in the current implementation of Linux, both I/O rings and DMA buffers are allocated from the secure memory of S-VMs. As shown in the figure, the PVIO backend in the N-visor can directly access the shared I/O rings and DMA buffers of an N-VM in the normal memory. However, the I/O rings and DMA buffers of S-VMs are in the secure memory, which is inaccessible to the N-visor. TwinVisor addresses this issue by duplicating I/O rings and DMA buffers in the normal memory for the N-visor. It synchronizes I/O requests and DMA data between the normal world and the secure world for shadowing. Unfortunately, the shadow PVIO brings non-negligible overhead for network-intensive applications. To reduce the network I/O latency, TwinVisor piggybacks some synchronizations on routing VMXs caused by WFX instructions and physical interrupts. We implemented two prototypes, one on the official simulator ARM FVP with S-EL2 extension enabled for functional evaluation. Since there is no commercially available hardware supporting S-EL2 at the time, we implemented another prototype on HiSilicon Killing N-0, a development board with N-EL2 enabled for performance evaluation. Note that Killing N-0 works similarly to the S-EL2 enabled hardware. As for the code effort, the S-visor only consists of 5,800 lines of code. For the trusted firmware, we have to add much code, about 1,900 lines of code, to support the S-visor in the N-EL2 on Killing N-0. But if the hardware supports S-EL2, we just need to add 163 lines of code. Next is the performance evaluation. Our testbed configurations are shown as follows. To avoid performance instability brought by the asymmetric multi-core architecture, we only enable 4 cores of the same type. First is the Microbenchmark. The figure shows the breakdown of hypervisor primitives. For a null round-trip hypercore, with fast switch, the time cost of a hypercore decreases 3,374 cycles compared to disabling fast switch. Eventually, TwinVisor incurs 2,386 cycles more than the vanilla, resulting in 73% overhead. As for the Stage 2 page fault handling, Shadow S2PD adds 2,043 cycles to a Stage 2 page fault and results in 38% overhead. Next is real-world applications performance. The figures below show normalized performance of an SVM with 512 MB memory compared with vanilla. From the left to right, the SVMs equipped with 1, 4, and 8 vCPUs. The maximum average overhead of all applications is no more than 5%. Such small overhead is due to the fact that wall switches occupy merely a small proportion of applications' effective execution time. For scalability, we also evaluate the memcached and the mixed workload with the increasing number or size of vCPU, memory, and SVMs. The maximum overhead is no more than 6%, which shows that TwinVisor performs well enough with the growth of hardware resources. We further evaluate the overhead of memory compaction operations of Split CMA. As shown in the left figure, the throughput of memcached in a single SVM drops by 6.8% in the worst case when 512 MB memory is migrated. In the case of 8 SVMs in the right figure, the average throughput of an SVM only drops by 1.3% in the worst case. The overhead decreases because our compaction overhead is amortized by multiple SVMs. To conclude, TwinVisor enables hardware-isolated confidential VM on ARM platforms. The key insight is to retrofit existing TrustZone with software designs by decoupling protection from management with 3 major techniques. According to the evaluation, TwinVisor achieved comparable performance to vanilla in various benchmarks. Our design also provides references for future systems with a similar architecture, such as dual hypervisor systems atop ARM CCA. A prototype of TwinVisor is open sourced on GitHub. That's all, and thank you for listening.